quite different things, but they're very similar technologically. Both of them use L-band microwave. L-band is a very low-frequency microwave, and unlike infrared and visible, you can just sort of say what the spectrum is in microns. They have all these Ka, Ku, L, P, W bands in the microwave. But the point is that the L-band requires to have a good resolution on the ground. You have to have a big antenna. So these things have these sort of disc antennas, and they're pointing to the disc antenna and then looking at the Earth. So let's talk a bit about microwave emission from the Earth. If you take the emissivity plus the reflectivity, equals 1. All right. So when you get microwaves from the Earth, especially in low frequencies, basically it's all coming from emissivity of different soil types, the ocean, all kinds of things. If the ocean has got a different salinity, it has a different emissivity. Okay, so what's the reflectivity? Well, what you're reflecting is basically the black body temperature of the universe, which is 3 degrees Kelvin. So that's why this works, because the radiation coming from the black body explosion, the Big Bang, is so weak in these wavelengths that we can measure emissivity directly from the planet without worrying about what's shining down from the cosmos, because it's almost nothing. All right? So we can look at different soil types, do all kinds of things in the microwave, in L-band microwave. These missions actually have two kinds of instruments on board. An active instrument, which sends a pulse down and gets a reflected pulse back, and a broader instrument, which has got a swath to look at just the pure emissivity. And they calibrate against each other. So one is using the active pulse to get a sort of absolute measurement, and then you're using the passive instrument. Once you know that value, you're extending the capability outward to either side to get a broader swath. And you can use soil moisture. Soil moisture is measured in the microwave, and this links to the salinity links to global ocean circulation. And soil moisture, turns out that if you have a good measurement of soil moisture, you can extend the predictability of current weather models by about a half a day. Why is that true? Well, what happens is when it rains, as you know around here, if you watch the weather, like I always like to do, it rains, and then the next day the soil's really wet, and the sun comes out, and you got a lot of clouds, and you get rain the next day. Where is that water coming from the next day? Well, it's coming from the ground and evaporating upward and then reprecipitating out. This happens a lot, especially in this area, and as you go toward, almost in a straight line to the Gulf of Mexico, especially in the summer. So the current weather models don't really take into account the storage of moisture in the soil, and so they have a poor job of predicting precipitation when the soil is wet. And so this kind of measurement, which eventually will move over to the weather people, is able to make a measurement of soil moisture under a variety of conditions. The Army's very interested in this as well, because mud. You know, the Army really is interested in mud. Where is it? How thick is it? Is it really bad? Do I have to get out can I go through regions in the desert that are now suddenly muddy because of rainfall? So this has got some other homeland security uses, as we say inside the Beltway. Okay, so this is our current picture of years and years of ship observations of salinity. Okay, you can see there are huge areas where we really don't know much about salinity. These are sort of the economic tracks of ships that make voyages around various cities. This would be 1 month of Aquarius measurements. So we're really gonna, this is a new frontier, this salinity measurement. And why is it important? Well, the reason it's important is because of the thermocline, ocean thermocline circulation. And what happens in the ocean is this. In this little region of North Atlantic, ocean water gets salty enough to actually sink. Okay? And so it sinks and it travels around here, eventually rises back up in the North Pacific and warms around and comes back around this way. The key for the ocean water to sink in this region, this is the 500-year time scale circulation. This isn't quick by any stretch. But this circulation is a major source of, for example, bringing nutrients up here, for keeping you have warm water coming up in here. Who saw this crazy movie, The Day After Tomorrow? Did anybody see that? Okay. This is what they were trying to talk about, but of course it's Hollywood. They never get anything right in Hollywood. But that's what they were talking about, is the shutdown of this thermal haline circulation in the North Atlantic. It would take years for such a thing to happen, and the weather response would never be that quick, but it made a nice movie anyway. And of course, we were told at NASA that we couldn't talk to any reporters about the movie because we work for the executive branch, and anyway. So actually that made a bigger stink than us actually talking to reporters, the fact that the press reported that we couldn't talk to reporters. Nonetheless, the point is that there is an issue in some climate models where this shuts down. As you get warmer and warmer, you get rid of sea ice. Why does it get salty up there? Sea ice forms. Sea ice forms as pure water, and therefore the salt is dumped out back into the ocean, and it gets really salty, and it's really cold, and so it sinks. Some of this sinking occurs down here too, not much, but the point is this circulation could shut down, and that would change the whole ocean system significantly. And it would also destroy fishing up in here. It turns out that because of this is something really interesting, I didn't know this until recently, but because it's sinking, the thermocline is very, very flat in this region. So there's a lot of turbulent mixing, and actually nutrients are brought upward in this region because of the turbulence. It's deep in this region. The mixed layer depth is really, really deep. And so that's actually what's bringing up a lot of nutrients for fish in this region. So if this thing shuts down, the fishing industry, which is already pretty much devastating one species after another off the coast of North America, would really be in trouble in this region. So there's a big economic issue as well as a climate issue associated with this problem. So we're able to quantify basically what's going on much better rather than a few of these ship observations in this region, and understand better what's going on in the Antarctic and in its own circulation. There is evidence that this did shut down in the past and it actually occurred down here. The sinking motion occurred down here in Antarctica. It's in the ocean sediment record. So it's a very interesting problem. Okay, so why measure soil moisture? Soil moisture provides water for vegetation, a strong link to the carbon cycle, improves precipitation predictions. Soil moisture measurements. This is an L-band polarization radiometer, and I've talked about how we really need soil moisture. So this would be a really cool measurement to make in this. And this spacecraft rotates, producing this swath like this, so it gets much bigger coverage than the salinity mission. But actually, they might be able to make a measurement of salinity too with this system. Okay, so GLORY is the spacecraft with another polarization instrument for aerosols, but also solar radiance. And I talked about the sun already. Here's the actual measurements of solar radiance that we have from previous missions. Lots of different ones up here. And some people think there's a trend. If you take the bottom here, this is the solar cycle, by the way. This U-shaped structure is the 11-year solar cycle. When the sun gets really quiet, these noisy things disappear down here. And you can see they're really flat at the bottom. And Dick Wilson, who flies the Akron instrument, has published a paper where he thinks that there's a trend by linking the bottom. Other people say, well, wait a minute, you ought to link the top too, and then if you do that, you don't get any trend. So there's some controversy about this. But this change in solar constant over a solar cycle is about 0.15%. It's really tiny, okay? So why do these guys all disagree with each other? Well, this is the difference between what we call accuracy and precision. This is a very, very precise measurement, but it's really hard to get accurate. So once you get an instrument up, you get a really precise measurement, but the accuracy is really kind of off. So these are only 2 watts per square meter, so we're not too far off between these guys, but still it's kind of annoying that we haven't quite settled on what the right number is. But this is an important measurement to continue because there are a number of people who think still that global warming is a result of something like this, even though this is a tiny number. Remember my original plot I showed you, temperature versus solar radiance? You know, the temperature doesn't change that much with the solar radiance, so this is really, really reaching to say that this is responsible for the warming. The last mission I'm going to talk about is global. I'm going to talk about this, I'm going to show a short movie, and I'm done. The Global Precipitation Mission, or GPM. And this is basically a question of measuring the hydrological cycle. It follows on the Tropical Rainfall Measurement Mission TRMM. And it's a radar in a high inclination orbit, but a bunch of radiometers with it. And here's the issue. This is 1900 and this is 2000. And people are claiming there may be a trend in precipitation over the United States. Looks like it's increasing. And the precipitation anomalies seem to be more intense. We're having more intense rainfalls. So we really don't know what's going on. Is this a climate shift? Is this a natural thing? Is this maybe better measurements, better rain gauges? You know, this is really kind of an interesting question. We don't know what's going on here. So this kind of shows TRMM observations. And you can see here, this is masked with cloud observations, and the colors in here indicate the intensity of the precipitation inside the clouds. And one thing that you can see is that very clearly, you wouldn't know which was more intense and which was less intense by looking at the top of the cloud. So you really need a radar to penetrate and determine what the precipitation is. And this mission was just in the tropics. And this should come up here. There it goes. So the GPM mission basically consists of a mothership here and a whole bunch of radiometers which are launched on satellites of opportunity. So we have this core satellite with a big radar on it, probably provided by Japan, and then these network of 8 satellites. So you get a 3-hour coverage everywhere. So that's the main idea behind GPM, and we're hoping to launch that in 2008. So now, at the end of my talk, I'm going to show you a very short movie. It's about 7 minutes long, that my wife and I made for the GEOS Summit, which was a summit Sean O'Keefe came to and showed this movie to the various international people who were there all over the world to put together a program of Earth observations. And I think I've got this plugged in, so you should hear some sound. Let's see if I can get it to work here. Yeah. So I'll let you watch this. That'll be the end.
For the forecast. There are several major environmental alerts affecting our world. Let's begin with Hurricane Gary in the Atlantic. As predicted, the outer rain bands of Gary generated 3 inches of precipitation overnight for Havana, Cuba. Gary is continuing to strengthen off the coast of Florida. The Weather Service's high-resolution ensemble models agree that the storm will not strike Orlando, but will move inland near Charleston, South Carolina. Here's the forecast loop. Now, we're looking at the best and worst case scenarios which could affect the East Coast. In the worst case scenario, we'll receive 8 inches of rain as Hurricane Gary stalls over Virginia Thursday night. In all cases, we expect clearing by Saturday. We expect lowland flooding and stream flooding in the Chesapeake and Potomac basins. Additional flood information can be found on the Emergency Information webpage, key to your location. We expect several days of severe air stagnation in the Northeast before the hurricane reaches that area. Air quality models predict ozone and particulate levels in the unhealthy range. If you suffer from respiratory problems, you should check the air quality website. In other environmental news, dust storms are predicted to move out of North Africa in the next week, affecting southern and eastern Europe air quality. An even larger event is predicted to develop in northern China later this week. Medium-range climate models show the current East Pacific Ocean warming will develop into a full-blown El Niño within 6 months. There's a high probability that drought conditions will occur in western North America and throughout South American rainforests. Updated soil moisture and crop forecasts for the next 6 months can be found at agriculture websites key to your location. Space radar indicates increased stress on faults in the California Mammoth Lake area. Earthquake models predict 5.0 to 5.5 magnitude tremors within the next few weeks. The USGS website has additional information on the earthquake forecast and safety procedures. Alaska's Mount Spur continues to erupt. The eastward drifting plume poses an aviation hazard to trans-Pacific flights. International flights have been rerouted around the plume. Be sure to check airline schedules.
What you have seen is our vision of the future. We will be using advancements in Earth science and observations for many practical applications. We will be making accurate predictions of climate change, crop production, energy and water use, disease outbreaks, and other natural hazards. What will it take to make these predictions? More observations of the Earth's environment are needed. More accurate measurements of winds, water vapor, temperatures, aerosols, and soil moisture will improve our forecasts. At the Lagrange points, Sentinel systems using lightweight holographic telescopes and interferometers will image the whole globe. From geostationary orbit, high-resolution optical and infrared sensors will monitor clouds, water vapor, ozone, and aerosols. In near-Earth orbit, LiDARs will measure winds, cloud heights, and ocean circulation. Microwave sensors and radars will measure soil moisture and ocean salinity, while synthetic aperture radars will measure earthquakes and rainfall. In the atmosphere, robotic aircraft will be deployed into severe storms. At the Earth's surface, a linked network of global sensors will monitor radiation, air pollution, precipitation, soil wetness, and stream flow. Beneath the ocean surface, undersea floats and robotic vehicles will measure salinity, temperature, and currents. We also know that better environmental predictions require realistic, high-resolution models. Prediction models assimilate all available satellite and ground observations to begin a forecast. The models then blend in information about ocean circulation, surface hydrology, cloud dynamics, and other processes. High-resolution prediction models of the future will produce precise local forecasts. These models will use and generate an enormous amount of data. How will future computers process and distribute this flood of information? As fast as computers will be by 2020, a single computer will still be thousands of times too slow to make accurate, detailed, local predictions. Forecast models of the future will run on teams of computers distributed across high-speed networks and linked to satellites through microwave and optical relays. Models on these distributed computers will be coupled to perform real-time local predictions. The output from the various prediction models will automatically be fed into models of flood prediction, crop forecast, transportation routing, energy use, as well as economic impact. These predictions will be available worldwide, and you will be able to tailor the output from these models for your specific needs. You'll be able to call up a personalized forecast from anywhere on our planet. This is our vision of the future. This vision harnesses the world's scientific and technical knowledge to protect our planet and improve the quality of our lives. Working together, we can make this vision a reality.
mission not only touches home, it's about home. It's about this planet. To understand and protect this home planet.
Thank you.
I'm sorry we went a little over, but sure, I'll entertain a few questions.
Yeah, we're gonna have some questions. I'm gonna turn the lights on a second.
Okay.
And then we'll give you a microphone.
I think you don't need a microphone. I might add that the current NASA administrator is under a cloud investigation right now. Not for starring in this movie.
My question, is NASA responsible? There's a lot of instrument and sensor technology here that must be developed, I suppose. Does NASA do most of that themselves, or is this somewhere else that they handle a lot of this?
Well, it depends on a lot of things. We do some of it ourselves, and we do some of them in partnership with industry. Usually what happens is NASA pioneers new technologies and then hands them off to industry. So a lot of the sensors that we have here, very few of them are built in-house. But the technology design, engineering design, and some of the technology elements that go into those designs are developed at NASA. One of the issues has always been with federal funding is how is that different from, say, corporate funding? Corporate funding is very targeted towards specific profit-oriented applications. The corporation doesn't see how they can make money off of the technology in the short term. They probably don't develop it. NASA, on the other hand, being a federal agency, has historically kind of gone after sort of the higher risk technology developments or pushed the envelope a lot harder. So a lot of the sensor development in chips and arrays and stuff like that we have in a lot of the satellites now were originally developed by NASA and are continuing to develop. We push a lot of that chip technology for imagers and things like that. No one else seems to want to do it. CCD arrays are great for TV, but you want a CCD array that operates in the 1 to 12 micron range. Nobody's interested in that. Maybe they will be interested in it, but NASA sort of does that kind of stuff. Or a lot of the microwave technologies now are being developed at NASA, both at Goddard and at JPL. Does that answer your question, Jim?
You quoted Jim Hansen. He's made a statement, I think it was in Scientific American, that if we reach a watt per square meter, that's enough to set in motion some massive melting. We're at 7/10 now if you add the year 2 to the cooling and warming you mentioned. And the one aspect that he says we have a hope of limiting on the warming side is black carbon. But you didn't say too much about, it would seem to me that would be a priority to be able to measure and monitor black carbon and see if in fact we could create some public policy with regard to black carbon and measure and see if we're doing anything. But what's NASA doing in that, specifically in that part of the Earth?
Well, the APS instrument, which I talked about briefly, mostly as far as the total solar radiance, we'll be able to measure black carbon. It's got a really crappy footprint, though. And I think it's more of a pioneering proof of concept measurement. The Polder instrument might be able to do the job. I and a guy named Yoram Kaufman, because there was some work, proposed an instrument a while back to look at black carbon by looking at the sun glint. The sun glint is really an interesting thing that's been underutilized or underused by most of remote sensing people. It's basically a source of radiation at the surface which shines through the atmosphere. So black carbon would intercept that radiation and you could see its effect. And you can often see it just going out and looking at a glint off a lake. It's yellowy kind of, it's sometimes colored, and that's because of stuff in the air that it's passing between the glint and your eyes. But let's go back to the black carbon problem again, just for the beginning. Black carbon is a very interesting problem because, as you can see, that black carbon is doing damage to the hydrological cycle and also heating the atmosphere. And what we have now, what we think is a balance between aerosols sort of masking the effect of CO2. But black carbon may be not helping aerosols mask the effect of CO2. And we really don't know how much black carbon there is, and we don't know how much an impact it's having. We do from models. There have been a number of studies. One study showed that, for example, that the Europeans who've moved to diesel are actually hurting the environment more than if they were still using gasoline, because the black carbon they're emitting is having much more of a climate feedback than the carbon dioxide that they're saving by going to diesel. Ironic. And another thing about black carbon, and this is where Jim Hansen's point is it's probably technologically a lot easier to control black carbon than it is to do anything else. Black carbon comes from two-cycle engines and biomass burning and smoldering fires and stuff like that. So if you get rid of the two-cycle engines in a lot of cities and a lot of places, you really lower the black carbon quite a bit. We don't have much in the United States because we have mostly four-cycle engines. But you go to New Delhi, or you go to Sao Paulo, you find these really noisy little engines in the street, and those things produce a whole lot of incomplete combustion, which is a source of black carbon. So there's a lot of issues. Unfortunately, the science community has been kind of slow to pull black carbon out, and it's a difficult measurement to make. And one of the problems with satellite measurements, you kind of saw the long timelines on some of these things. I've been working on Aura, which was launched this year, for 10 years. We knew what the payload was 10 years ago. Okay? To get the money together and just do it, it takes a long time. The fastest I've seen stuff come together is 3 to 4 years. So for us to respond to an orbital mission is going to be downstream. I think we need to take and use what we've got in orbit and fund working on that to see if we can pull the black carbon signal off. That's where I think we need to go right now. We can't address this quickly from space, but we're trying.
So, one more question, I think, and then there's treats in the back.
Oh,
And you'll be able to continue to talk with people.
sure.
Go ahead, Peter.
What percentage of the satellites that you put up actually work as they are supposed to?
Well, it depends on what you mean by work as they're supposed to.
It's an open-ended question, isn't it?
Well, we have a really good success, if the satellite makes it in orbit, which doesn't sometimes happen, we made an instrument called Quiptrons, which is now measuring salinity. Instead of ozone. It failed to get into orbit, but we have about a 98% rate of getting things into orbit. We're really pretty good at it. The Air Force and the Navy do as well as we do. I think because we spend more money making sure things go off. Typically, we have about the same success rate as you have for any complex instrument going up. In Aura, we have all the instruments are working, for example, but we have a partial problem with one of them. We'll still get measurements out of it, but it isn't working as exactly as designed. But it's still working, and we'll get data out of it. The only other instrument on EOS that's totally failed at this point, well, two of them have failed. HSB, which I mentioned, has failed on Aqua. All the instruments, and Moffett, which is a Canadian instrument on Terra, has partially failed but still getting data. And we've had an instrument called, the ISAT instrument has had a problem, and that has to do with laser lifetime. It turned out that the lasers, the emitters, diode emitters, sat in a clean room for a long time, and they grew tiny tin whiskers while they're sitting there. And the tin whiskers shorted out the diodes after we got up in orbit. And we spent a lot of time trying to figure out what happened. All of a sudden, the laser power started to go down. So, but we have enough data from that that before it's kind of died, it's now sort of dead. We got enough data from that instrument to, I would call, mission success. So it's hard to sort of define what you mean is, right out of the box, we do pretty well. After a year, these instruments start to fall apart. But then we have some spectacular successes. The spacecraft was launched in 1985 and it's still producing data. I mean, that's a geriatric spacecraft. I mean, space is a really harsh environment, and things start to happen. The solar rays start losing power, the batteries get old, all kinds of things break. Imagine you're driving down the road. This is the way you treat it as a spacecraft. You're driving down the road and something happens and your car stops. So what do? Well, suppose the only thing you could do is turn the radio on and off and roll the windows up and down. Well, we tried that. Okay, and then sometimes it works. The car starts up and it goes. But mostly we can't do much to fix stuff in orbit. It's broken. And it's an interesting business. And making a spacecraft, designing a spacecraft to live 6 years is a lot more expensive. Even 10 years is almost impossible to build a space. I mean, those are one of the reasons that the mission to Saturn was so expensive is the long time it took to get there. That thing had to survive a long time. And so that cascades down into making the parts really, really perfect and testing them to the nth degree. And as a result, that's a lot of person time and the mission cost goes way up. So it's a complicated business. If you want to have a satellite that works 6 months, it's easy to build, they're cheap. But who wants 6 months when you're talking about climate? Not me.
I think we give Mark a big round of applause for very much. Coffee and punch and brownies, and people I'm sure he'll be willing to talk to you and come up and ask him some more questions.
That's right, again, continue